Welcome, Algebra students, to our video notes on section 2.7, which is focusing on the multiple forms of quadratic equations. So something I want you to think about in this video is, how do we know if an equation is quadratic? What will be the sign that helps us go, oh, this must be one of those forms of a quadratic equation? Well, we will know if the highest power of x is 2. So these are the three different forms you may see a quadratic equation in. And every one of these forms has x squared. Okay, the highest power is x squared. There's nothing higher. There's no x cubed, x to the fourth. And there's more than just x to the first. It includes a power of 2. So it's the highest power of x in the equation. In standard form, you can see it right away. We have an x squared, so that lets us know it's quadratic. In vertex form, we can tell because the parentheses around x minus h are being squared. That means the highest power of x is 2. That means this equation is quadratic. In intercept form, we have two binomials being multiplied together. That's how we know x is going to be squared, because if I were to FOIL them, I'd have to do x times x. When you do x times x, you get x squared, right? There's no third factor of x. There's just two. Two binomials being multiplied together, each with an x and an x, are going to give you a power of 2, power of x squared. So that tells us it's quadratic. So depending on what type the equation is in, we will change our strategy a little bit in terms of how we graph them. So let's kind of focus first on this standard form here. Standard form is the one when there are no parentheses. So that's how you know if it's standard form. Because everything has been FOILed out, all the like terms have been combined, so there's no parentheses, just single terms, ax squared, bx, and c. And the unique feature, or the unique thing that this form shows us, is the y-intercept. Because since everything's been FOILed out and we have these different terms, c is the only one that doesn't have an x. So if I were to plug in 0 for x, I'd get a times 0, because 0 squared is 0. I'd get b times 0, because I'm plugging in 0 for x. C would be the only one of these coefficients that doesn't multiply to 0. Again, this is if I'm plugging in 0 for x. The a would go to 0, the b would go to 0, and I would just be left with c. So because of the way this form is written, then we can just see by looking at this constant c, the one without x, we can know that that's the y-intercept. So because this form shows us that so quickly, then when we're graphing it, that's one of the first things we use. So that would be like step 1 is to plot the y-intercept, because it's so easy to read from the equation. To not use it would just be silly. So we always use this point 0c. The other thing that this formula or this form shows us is a. This a that's in front of x squared is the same thing as this a from vertex form, and actually it's the same thing as this a that we see in intercept form. So you only need to write this a value part down once, because it's the same a value for all three forms. So basically the number getting multiplied to the x squared, it tells us what the shape of the graph's going to look like. So if it's greater than 1, it tells us, okay, it's going to be a vertical stretch, so the graph will be skinnier. If it's a fraction between 0 and 1, it tells us, okay, it's going to shrink or become wider. If the a turns negative, then it's going to make this parabola open down. Because if you remember, quadratic equations all make parabolas. So if a is negative, then the parabola opens down. So we should be able to know whether or not that will happen based on these a values, which again is the number in front of x squared. Okay, now the second thing we're going to do to plot an equation in standard form is to find the vertex. So we need to find it, because the equation doesn't show it to us. We have to find it, but we do have a formula for it. So remember, the vertex is an ordered pair, x, comma, y. So the first thing we do is find the x coordinate using this formula, negative b over 2a. The negative b and the a are coming from this standard form up here, where it's a is the one in front of x squared, B is the one in front of X, and then C is the constant. In this vertex formula, we're just using B and A. Okay? That will tell me what the X coordinate of my vertex is. So my vertex is going to end up being negative B over 2A, comma, and then the Y coordinate. How do we find the Y coordinate for the vertex? We have to evaluate this function, right? This standard form function. We have to evaluate it at whatever I got when I did negative B over 2A for X. I take that X value and I plug it into this equation. Each place there's an X. And that will tell me my Y coordinate of the vertex. So then that's what would be the second coordinate here. So I have to find this using the A and the B from the standard form. Then the third thing I'm going to do is sort of reflect the Y-intercept that I found from the equation, the 0C. I'm going to reflect it across the middle of the graph because the vertex, by the way, is the middle of the graph. So I'm going to reflect it across the vertex. And usually that's enough because that gives us 3 points. That gives us the Y-intercept, 0, C, the vertex. And then when you reflect the Y-intercept across that, it gives us a third point. But I'm going to add a step 4 here to squeeze it in here. You are also always welcome to just plug in some X values to the left and right of the middle. That is always an option, especially if you're kind of not 100% sure what to do. But it's really helpful to find that vertex. It's really helpful to find the middle. So I want you guys to memorize this formula here. The negative B over 2A finds the X, and then you have to plug it into the equation to find Y, and together X comma Y makes the vertex, which is the middle of the graph. Okay, we always want to remember that too. The vertex for a parabola is the middle. So let's try that now with example 1. So the form of equation we have in number 1 is standard form. And the way we can tell it's in standard form is because it has no parentheses. So that is the kind of giveaway or the clue that the equation you're working with is in standard form, because it means everything's been multiplied out and all the like terms have been combined. So in this form, the Y-intercept becomes really obvious because it's the only number left without an X. So it's our C value. So that is how we begin graphing something in standard form, is we plot the Y-intercept, which in this example is 0, 1. So I am going to add that to my graph first, and it'll be right here. Then the second thing we do is we find the vertex. So when the equation is in standard form, the vertex is not readily obvious. So instead we have to use the formula given above, where X is equal to negative B over 2A. So in this example, A is 3 and B is 12. So plugging them into this formula, I get negative 1 times 12 over 2 times 3, which is negative 12 over 6, which is negative 2. So that is the X coordinate for the vertex. So we're halfway done with finding our vertex. We've got the X coordinate and now just have to find the Y coordinate. So how do we find the Y coordinate is we take that X value that we just found and substitute it into our equation wherever X is. So we find F evaluated at negative 2. So I would do 3 times negative 2 squared plus 12 times negative 2 plus 1. And then we follow the order of operations. So I have to square the negative 2 first before I multiply 3. And when I square negative 2, I get 4. And then 12 times negative 2 is negative 24. And then I add 1, so then I get 12 minus 24 plus 1, which is negative 12 plus 1, which is negative 11. So that is the Y coordinate of the vertex. So together, if I put negative 2 with negative 11, that gives me my full vertex. So then I'm going to go ahead and plot that point as well. So -2, -11 goes a little bit off the grid, be like right there. And that gives us our middle. So then the third thing I do is I reflect the y-intercept across the middle, because the graph of a quadratic equation, which again is when the highest power of x is 2, forms a parabola. And what we understand about parabolas is that they have symmetry across the middle. So the points on the right are a reflection of the points on the left of the middle. And the vertex locates the middle for us. So we know that the vertex will always be in the middle. So maybe I'll draw a little dotted line that goes through the x value so that we can kind of visualize it. So I can see that this y-intercept is 2 spaces away from the middle, and it's at a y value of 1. So if I use that symmetry and I go 2 spaces to the left, I should have another y value of 1. So that would give me the point -4, 1. So now I have 3 points on my graph: 0, 1, -2, -11, and -4, 1. And 3 points is sufficient to make your graph, as long as you remember it's going to be a parabola, not a V. Right? Sometimes it's tempting, especially when these points are so far away, to just make straight lines connecting them, but this is not an absolute value function, this is quadratic, so we have to round it out around the vertex. So it would look something like that. Now if you look at this graph, it looks very tall and skinny, and that actually is an indication that we did this correctly, because look at my a value here. My a value is 3. So when a is greater than 1, which it is in this case, that means that we're going to have a vertical stretch, right? When the a value is greater than 1, the graph should look like it's been vertically stretched, which has the effect of making the graph look skinny, right? And this does. It looks kind of tall and skinny. Also, the a value is positive because it's 3 positive. So it does make sense that our graph is opening up. These are all kind of things we want to check when we're making our graph. So I'm feeling pretty confident that this graph is correct, just because everything sort of matches up. So now let's go ahead and find some of these defining characteristics down below. So one of the things we want you to find are the x-intercepts, and we haven't yet covered how to find them exactly, because that's coming in our next unit, but we can at least look at the graph and kind of estimate where they are. So looks like there would be one that's really close to -4, and then looks like there would be one really close to 0. So we could estimate and say that probably it would be somewhere around -3.9, because it's almost at -4, and looks like it'd be maybe -0.1. Of course, there is a way to find exactly where they are, but we just haven't taught that yet. So right now we're just kind of looking at the graph and sort of estimating. Now the y-intercept was given in the equation, right? This is standard form, so that's when we just know that the y-intercept is going to be whatever c is, which in this case was 1. So we will write that as 0, 1. Actually, let me write these x-intercepts the same way. So I should write it as approximately -3.9, 0, and -0.1, 0. Again, these are not exact, but approximate. Now the vertex we found through using the -b/2a formula. So that was -2, and then we plugged that in and found -11 for y. And then that helps us understand what our range is. So our range is when we're looking at all the possible y values along the vertical axis. And since these arrows are going up, it looks like the y values, all the y values from -11 and up are included on this graph. I have points for all of those y values. So my range would be from, I would use the bracket, from -11 up to infinity. Or you could write that as y is greater than or equal to -11. The domain for any parabola is always all the way from -infinity to infinity, because it's always all real numbers. Because the shape of a parabola, whether it's opening up or down, it always has these arrows at the end that go at sort of these angles. So it always goes left and right forever. And same if it's facing down, it still goes left and right forever, just sort of at an angle. So the domain for these graphs will always be all real numbers. And also for parabolas, which is what the graph of a quadratic equation looks like, there's always just the one turning point. It was right here in this case because it's wherever the vertex is. So that's what this has. It has a vertex. And then in this case, since the parabola was opening up, and it was opening up because A was positive, then this graph has a minimum. And the minimum value was -11. That was the lowest value Y could have. And again, that's because this graph opened up. So it has a minimum versus a maximum. And that was because A was positive. Also because A was positive, the arrows on both ends point up. So that means that when X is on the left and on the right, so -infinity and positive infinity for X, Y is going up. So that's positive infinity for Y. And we can see that right here on this side and on that side. And the increasing interval is, in this case, is on the right side of the middle. So remember, when we're talking about increasing or decreasing, we are reading the graph from left to right. So starting from this side, we kind of read it and then we go all the way to this side. So, or the right side, which is when X is approaching positive infinity. And I noticed that if I was writing on this graph, I would be sliding down it as I go from the left side until I get to the X value of -2. That's where it hit the minimum and turned around and began to go up. So I would say from -infinity to -2, the graph is decreasing. And then at that X value of -2, it hit a low point, it turned around and began to climb. And that was for these X values, from -2 moving toward infinity. The corresponding Y values from that point on are rising, they're increasing. So that would be my increasing interval. And yes, this is a function because it passes the vertical line test. So if I were to draw a vertical line through it at any point, it would hit only once, which means it passes the vertical line test, which means it's a function. And it's definitely not one-to-one because though it passes the vertical line test, it fails the horizontal line test. If I draw a horizontal line at multiple places on this graph, it'll hit twice versus once. So for the evaluating part, I kind of wanted to add some more points to my graph because that's what evaluating a function does. It helps you find more points on the graph. So let's evaluate a couple points to the left and right of the middle. Let's find f of -3 and f of -1. So let me do that up here actually, because I wanted to remind you guys there's actually a fourth step. It's kind of an optional step, but it's what you can use if you're stuck or you're not sure or you just want to confirm your graph, and that is to plug in X values to the left and right of the middle. Let's go ahead and make one last little table here. And I'm going to plug in -3, which was to the left of the middle. Remember the middle was at -2 and then -1. So f of -3 is what I get when I plug in 3 for x into the equation above. So it was 3x squared plus 12x plus 1. So I'm just substituting in a -3 there. And then I have to use order of operations. So I have to square the 3 first, which is +9, and then I'll multiply by 3. Here I multiply 12 to -3 and get -36. And then when I multiply 3 to 9, I get 27. So then 27 minus 36 gives me -9. And then I add 1 to that and get -8. So f of -3 ends up equaling -8. So let's see where that would be on my graph. And maybe I'll take away some of these green arrows here. Okay, so my point -3, -8 would be at right here on my graph, which is confirmation because it looks like my graph is going to that point. That's a good sign. And so let's find f of -1. So to do that, I just plug -1 in for x into the equation above and use the order of operations. So I square the -1 first, it becomes positive. I multiply 12 and -1, get -12. So then this becomes 3 minus 12, which is -9, plus 1 is -8. So it looks like f of -1 was also equal to -8, and that makes sense because since they're evenly spaced across the middle, they should be symmetric. And so what we were able to do by just plugging in some x values to the left and right of the middle was get a couple other points on the graph just to help us get a really full picture, or even just confirm that the graph we had was correct. So it's an optional step 4, but it's really helpful. And for these notes, I just used those points as part of the evaluation example to kind of tie it all together. Okay, so the next form of a quadratic equation is the vertex form. And the giveaway sign that you're in vertex form is when you have a parentheses squared. That is when you know you're in vertex form of a quadratic. So what are the pieces that vertex form show us? They show us h and k, which is the vertex. So from vertex form, without having to do any work, we know what the vertex is, which is a very nice feature of this form. So to graph the equation, we basically use the graphing transformations. We use the same process that you were taught in the last section. So this is where we say, okay, the parent function is y equals x squared, and the table of values for that, if we use those typical x values for the parent function, -2 to 2, and if y is squaring them, then -2 squared would be 4, -1 squared would be 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So this is when we take just the parent function and the y coordinate is just x squared. But then we are going to use the a, h, and k values that are given in hk form to make a transformation table. So then this converts to x plus h, whatever h is, and then a times y plus k, whatever a and k are. So for these x's, you basically just take all of them and add h to them. And then for these y values, 4, 1, 0, 1, 4, you multiply each of them by a and add k, whatever a and k happen to be for each of the equations. So we basically will do that for anything that's in vertex form, which again is when you have the parentheses squared. And then you can still, so I'll say step 2, I guess. So step 1 is to use graphing transformations. Step 2 would be similar to our step 4. You're always welcome to plug in x values. So we'll look at that too. It's kind of like an optional step. And I'm going to kind of repeat what this says. Plug in x values to the left and right of the middle. That was kind of a 2.2 strategy that never goes out of style, right? Even when we start learning other techniques, that's always a good style. And remember, since vertex form shows us the vertex, and since the vertex is the middle, that means h, right? H is the x-coordinate from the vertex. That is showing you the middle of this graph. So if you pick a couple values to the left and right of h to plug in, that'll give you some really good points on the graph. So it's always an option. Let's try this one. So the vertex form example in this handout is actually all the way down here at example 3. Why was this the one in vertex form? It's because this is the one that has the parentheses squared in the equation. So this is matching the a parentheses x minus h squared plus k form, because it's got the parentheses squared. So I can see that a is going to be negative 0.25. So that's another thing, is I know that this graph is going to open down because my a is negative. And I can see that my h is 2 and my k is 6. So I also know the vertex of this graph should be at 2, 6. In fact, I'm going to go ahead and plot that point right now. So I should have a point at 2, 6. because that's the middle of my graph. Okay, so now what we're going to do using the AH and K is we're going to make a transformation table. So here's my parent table for x squared, right? This is the parent for x squared. Got to make sure you're using the right parent function. And then I'm going to transform all this. So I'm going to do x plus 2 because that was h. And then negative 0.25 times these y values, and then plus 6. So this will be negative 2 plus 2, negative 1 plus 2, 0 plus 2, 1 plus 2, 2 plus 2. So my x values are going to be 0, 1, 2, 3, and 4. And notice 2 is the new middle. It's the new 0 basically, as it should be because that's h, which is the middle. Now remember, negative 0.25 is the same thing as negative 1/4. So maybe I will write it that way so that I can see if I can multiply these easy. So I'm going to do negative 1/4 times my first y value, which is 4, plus 6. So that gets me negative 1 plus 6, which is 5. Then I'm going to do negative 1/4 times my second y value of 1 plus 6. So then that ends up just being, well, maybe it'd be easier to think of it as negative 0.25 after all, plus 6. And then that's 5.75. Okay, and then for the new middle, it's negative 1/4 times 0 plus 6. So that's just 0 plus 6, which is 6, as it should be, right? 6 is the new 0 for the y value. This is the new middle. It should be 2, 6. Okay, and then the other y values end up just being the same as these because, again, I find myself doing negative 1/4 times 1 plus 6. Right? We already did that earlier. That ended up being 5.75. And then negative 1/4 times 4 plus 6. We did that earlier. That ended up being 5. So I have the following points: 0, 5, 1, 5.75, 2, 6, which I already graphed my vertex, 3, 5.75, and 4, 5. So I'm just going to plot those points basically. So 0, 5 is here. 1, 5.75 would be like right there, close to 6, but not quite. 3, 5.75 would be right there. Again, close to 6, but not quite. And then 4, 5 would be like right here. So just as we suspected, this graph is opening down. And notice how it's kind of wider too. It's wider because A, so if you take the absolute value of A, and if that number is between 0 and 1, that means you have a vertical shrink. So because A was a fraction basically, so if I take the absolute value of negative 0.25, that basically is positive 0.25, which is less than 1 but greater than 0. So that means it's a vertical shrink. That means it should be wider than normal, which is definitely the case here. Okay, so now that we have our graph, we're going to go ahead and answer some of these questions. So for the x-intercepts, it's, again, we haven't learned how to find them exactly yet, but we can kind of look at them on the graph and maybe sort of estimate where they'd be. So on this side, it looks like maybe it's somewhere around negative 2, and on this side, it looks like maybe it's somewhere around 6. So I'm guessing here, right? These are not exact, but it looks like maybe it's around negative 2 on the left and 6 or maybe a little more than 6 on the right. My y-intercept we found actually, that was ended up being one of my table points, was 0, 5. But if I didn't know it from my table, I could always plug in 0 for x to find it. And then my domain, of course, is all of the real numbers because this is a parabola. My range is going to be based off the highest value here of 6. So 6 is like the highest y value, and then all the other y values on the graph are below 6. There's no points on the graph above 6. So we can either say y is less than or equal to 6, or we can say that the y values go from negative infinity up to 6, including 6. So we put a bracket. Again, this has a vertex, which was hk, right? So we use h and k to know that, 2, 6. It has one turning point, which is the vertex. And in this case, since the graph was opening down, it was a maximum point, and the maximum height of y was 6. Also, because this graph was opening down, because a was less than 0, we say that y is going to negative infinity on both sides. The left side when x is negative infinity, and the right side when x is positive infinity. Because it was going down, the increasing interval was actually on the left-hand side. So from the left part of the x-axis up until 2, the y values are rising along that interval. So we would say negative infinity to 2 for the increasing side. And then after you pass 2 and you're moving toward positive infinity along the x-axis, that's where on the graph the y values are going down. So that would be our decreasing interval. Is this a function? Yes, definitely a function, but not one-to-one, because though it passes the vertical line test, right, we can see that if I drew a vertical line at any point, it would only hit once, so it's a function. But if I try the horizontal line test, it fails. It hits more than once, so it's not one-to-one. So now I'm going to go ahead and evaluate. Maybe I'll plug in something over here like -2. Maybe I'll check the things I thought were the x-intercept. Maybe I'll just check and see what I get when I plug in -2 and 6. So that's what we're going to practice evaluating. F of -2 and f of 6. This is to the left of the middle, this is to the right of the middle. And I'll do the work for that right here. So remember, when I evaluate, I go back to the original equation, not the parent function, but the original function, the -0.25 x minus 2 squared plus 6. When I'm plugging values in, that's where I plug them into. I'm going to think of it though as -1/4 times x minus 2 squared plus 6. I'm going to go ahead and plug in -2 first. So I get -1/4 times -2 minus 2 squared plus 6. That ends up giving me -1/4 times -4 squared plus 6. Since both of these were negative, they actually ended up adding up to -4. And then I have to remember to square first before I multiply to the 1/4. And when I square -4, I get positive 16. So then -1/4 times 16 is just -4 plus 6 is 2. So it looks like my x-intercept guess was wrong. It looks like when I plug in -2 for x, I get 2 for y. So then the ordered pair for that one is -2, 2, not -2, 0. So I'm going to adjust my graph a little bit to make room for that point. Let's add these points on. So I'm going to plug in the point -2, 2. All right, and then if I plug in 6 on the right-hand side, then I get -1/4 times 6 minus 2 squared plus 6. That ends up being -1/4 times 4 squared plus 6. And so again, I end up getting -1/4 times 16, which is basically 16 divided by 4, but it's negative. So -4 plus 6 is 2. So I get the same thing. So for this point, I get 6, 2 as well. So I'm going to add that to my graph right here. And I think I'm going to make a different guess for my intercepts. Now that I have plugged in these extra x values, you can see how it kind of helps. I know my graph is going to hit the x-axis a little to the left of 6 and a little, oh, that doesn't look like a U. Here, let me fix this here. And a little to the right of 6. Sorry, still can't quite get a neat graph in there, but let's adjust our intercepts over here. Let's say they're not quite -2 and 6. This would be maybe -2.5 maybe, right? Eventually we'll learn how to find them for sure. But for now, and let's just say 6.5 for now. little to the left of -2, little to the right of 6. Okay, so that concludes example 3. So the last form that we have at the beginning of this outline is called intercept form. Sometimes I call it factor form because it's basically a quadratic equation that's been factored. Now we call these little numbers in here R1 and R2 because the name for these is called roots. Sometimes they're also referred to as zeros, and they end up being the x-intercepts of this quadratic on the graph. So why are these the zeros or the roots? It's because if I were to take each of these factors and set it equal to 0 and solve for x, for the first one I would get x equals r sub 1. What that means is this is the x value that makes that whole entire factor equal to 0. And the same thing would happen if I set the second factor equal to 0 and solve for x. I would find that if x equals r sub 2, these end up being the values of x that cause these factors to be 0. So for example, if I were to plug it in, like if I were to evaluate f at one of these roots, I'll just say r sub 1. I'd have a times r sub 1 minus r sub 1 times r sub 1 minus r sub 2. Well, the a is just a number, right? Just some number. R sub 1 minus r sub 1 would be 0, right? And then r sub 1 minus r sub 2 would just be some other number. So I'd have number time, and they're all being multiplied, right? Together, one long string of multiplication. So number times 0 times number is just 0. Okay, so f evaluated at either one of these roots. The same thing would happen if I plugged in r sub 2. So if I plug in any one of these roots into the function, I get a 0. So that's why they're called zeros. That's why they're roots. That's also why they are x-intercepts, because what is f of something? It's the y value. So these are basically, r sub 1 and r sub 2 are basically the values of x that make y of this equation equal to 0. So we use them to make the graph. So the steps would be to plot our x-intercepts because we know what they are very easily from the equation. So that would be r sub 1, comma 0, and r sub 2, comma 0. So that would be step 1. But with all of these graphs, we want to be able to find the middle. So unlike vertex form and like standard form, I have to find the vertex. And I know what A is, right? Because this A is the same A as the other forms, but I don't know what B is. So instead, what I'm going to remember is that the vertex is the middle. It's the exact middle between these intercepts. So I can find the x-coordinate of the vertex by locating the middle of these intercepts. So I can take the average of the intercepts, and that will locate the x value of the vertex. And then to get the y value of the vertex, I just evaluate the function at that number I found. So once I figure out what this number is, this middle, I plug it into my equation up here for x, and that tells me the y value of my vertex. So I find the vertex and I plot the vertex, and then I'm done essentially because I now have 3 points. 2 intercepts and the vertex. But you always have this option of plugging in x values. So I'm going to just put that as an optional step 3. And you know, it's ideal to plug them in to the left and right of the middle. So finding the middle is always key. And vertex form shows you the middle. Standard form gives you a formula based on these coefficients in the equation for the middle. And intercept form, since it gives us these 2 intercepts, we can find the middle by taking the average of the intercepts. Okay, so let's try that with example 2. Also, I want to point out here with example 2 that I kind of changed it slightly from what it was originally in the note guide. So your note guide might still be showing the old one that had a 3 in front and then an x minus 1 over 3. So I'd like you to cross that out and write in our new equation, which has a 1 in front, and then x minus 4 is the same, and then I changed this to a plus. So it's x plus, and then I changed it to a 1. So 1 times x minus 4 times x plus 1. Please change it to that on your outline. Okay, now I say that this is in intercept form because it has 2 sets of parentheses. So that's why another word I use for this is factored form. It looks like it's basically been factored because that's basically what happened. It was factored. 1 intercept at 4 and 1 intercept at -1. You might be saying, Miss Lasner, hello, that's a plus. And I would say, well, I need to find basically the number for x that would make these 0. So here's how we find our x-intercepts. We set each of those factors equal to 0 and solve for x. Now notice, the factor is -4. So to get x to the other side, I have to add it. So notice how my x-intercepts, or my roots, are always the opposite sign from the factor. So one intercept is at 4, 0. And then the other one, so the factor was plus, x plus 1. So to solve for x, I have to subtract 1. So my other factor is -1, 0. Or my other intercept, sorry, my other x-intercept is -1, 0. So your roots, your r sub 1 and your r sub 2, are always opposite sign from what the factor is. If the factor is minus, your root is positive. If the factor is plus, your root is negative. So we plot those points. So that's step 1 is to plot our x-intercepts because they're super easy to see from the equation as long as we make opposite signs. So I have 1 at 4 and at -1. So then the second thing is to find the middle, right? Find the middle of the graph, which is basically the vertex, which is going to be the average between these 2 points, between 4 and -1. So I'm going to do the average. I'm going to add up the 2 numbers, 4 plus -1, and divide by 2. So that's 3 over 2, or 1.5. And if you look at the graph, that makes sense because 1.5 is smack in the middle between these 2 numbers. It's 2.5 away from this side and that side. So maybe I'll just draw my dotted line in there to kind of show the middle. So what is that? That's the x-coordinate of the vertex because it's the middle. So how do I find the y-coordinate? Well, I plug in that average, right? I plug in what I got when I did first root plus second root divided by 2. I got 1.5. I plug that into my equation, which means wherever x is, I replace it with 1.5. And so when I do 1.5 minus 4, I get -2.5. And then 1.5 plus 1 is +2.5, which makes sense because one number was 2.5 to the left from the middle, so that's the -2.5 one, and then the other one was 2.5 on the right of the middle, so that's the +2.5. So when I multiply that together, I get -6.25. So when I put those 2 points together, the x and the y, that makes the vertex. It's the ordered pair that forms the vertex. So that would be kind of right here, just below -6, and I have enough points there to do my graph. So there's my parabola, and it makes sense that it's opening up because we mentioned earlier the a value is 1. So since a is equal to 1, that's positive. That means our graph should open up. Okay, so the x-intercepts from this one we can find exactly because they were in the equation, right? That's why we call it intercept form, because it shows us the intercepts. So those were 4, 0 and -1, 0. Now the y-intercept we still need to find, so maybe we'll do that for our evaluation piece. I'm going to find the y value when x is 0. So I plug 0 into my equation wherever I have an x. So I get 0 minus 4 is -4, 0 plus 1 is 1. So my y-intercept should be at -4. So it looks like I goofed a little bit in my graph. Let me just clean it up here a little bit. And because parabolas have symmetry, and this is 1.5 spaces from the middle, I'm going to go another 1.5 on the other side and make another point at -4. So I'm going to draw my graph better now. I think that's the best one I've done this whole video. Thanks to the help of these other points. So anyway, that's my y-intercept, is 0, -4. So the domain, of course, is all real numbers, -infinity to infinity. The range is, so the lowest y value is -6.25. So the other y values are above that. So we would say from -6.25 to infinity for the range. Or you could say y is greater than or equal to -6.25. We read a bracket here to include that point. So this has a vertex at 1.5, comma, -6.25. That was our middle. It has one turning point, and it has a minimum since it was opening up, and the minimum is -6.25. Also, since it was opening up, we can say that the y value is going to positive infinity on both the left and the right end. So both of these are positive infinity. So that means, since it's opening up, that it was increasing on the right from 1.5 to infinity. So from here to the right, the y values are climbing. And then on the other side of the graph, from the left side to the middle, 1.5, the y values are decreasing there. So from -infinity to 1.5, and then yes, it's a function, no, it's not one-to-one, and we already did our evaluation piece. So we finally finished this video. Thanks for tuning in this whole time. You guys are amazing, and we'll see you in class.